So in this session, we are going to study filter functions in MATLAB. So let us start. In our previous session, we have seen how to obtain coefficients for low pass FIR filter analytically. That is, we looked at the ideal frequency response, took the inverse Fourier transform and found the coefficients. Now, similar technique can be used for high pass and band reject also. So you may try this at home. However, what I am going to do in this session is show to you which MATLAB function is available for calculating the coefficients for various filters. So you won't have to actually analytically solve it. Alright. So as I said, the equations for coefficients can be derived. But what we are going to do is to study MATLAB functions for coefficients of FIR filters. So this is how you call the function FIR1. So let's look at the input parameters. The first one is n, that denotes the order of the filter, number of delay elements in the filter. Then the normalized cutoff frequency, that will be specified in Wn. Then the type, whether it is low pass, high pass, band pass and so on. And the window, whether you are going to use a rectangular window function or Hamming window or something else. And when you provide these parameters to this function, what it returns is the array of B coefficients. That is the coefficients for the FIR filter. Alright, so let us look at each of these parameters one by one. As we said, n is the order of the filter. This corresponds to number of delay elements used. And thus the number of coefficients is n plus 1. Let me elaborate this a little by looking at this equation. Now you can have number of terms, but let us say assume that we got just 3 terms here, which means you have got 3 coefficients, that is B0, B1 and B2. So although the number of coefficients is 3, the number of delay units that are used are 2. As you can see, xn minus 1, this corresponds to a delay of 1 sample. This corresponds to the delay of 2 samples. So you got 2 delay units, but the number of coefficients is 1 more. So the order of the filter is number of delay elements. Now the window, it must have the length which is same as that of the coefficients. So its length must be n plus 1. Okay. Then the normalized cutoff frequency, this is normalized with respect to fs by 2, f divided by fs by 2. So you can write this 2 goes to the top and you can write it as 2f by fs. That is your Wn. Then the type, for low pass you write low, for high pass you write high, for band pass you write band pass, and for stop you write stop. There should be an apostrophe here before the band pass. Okay, what about the window? Now if you don't provide any specification here, then default is the Hamming window, which we studied last time. But there are other windows also, so you can use a Hamming window which is specified as Han n plus 1, or you can use a Blackman window which is n plus 1. And since the default is the Hamming window, if you want to use a rectangular window, you have to specify. So rectangular window is specified like this, n plus 1. Okay. So this is the filter function available. These are the input parameters and this is the output parameter from the function. Okay. So another important thing you should note is that when we calculate analytically these coefficients, we get values which are slightly different than the one that MATLAB provides. And let me explain why that is happening. So suppose you use a rectangular window and let's say number of coefficients is 3. And we saw last time for a low pass filter, this is 0.3183 etc. This is the first coefficient, this is the second, and this is the third one. But if you use the function that is available in the MATLAB for calculating the B coefficients, you will get slightly different values. And what is the reason for that? So MATLAB does the scaling so that the zero frequency gain is 1. Now, when you obtain the coefficients analytically, the zero frequency gain in general will not be equal to 1. And this gain, it's easy to show if you take the Fourier transform of both sides and put frequency equal to 0. It's easy to show that the gain for zero frequency is simply B0 plus B1 plus B2. So when these are the coefficients, the gain is simply the summation of these three terms and you get 1.1366. That is a zero frequency gain if you use the coefficients which were obtained analytically. Okay. But what the MATLAB does is it scales each value so that the final zero frequency gain that you get is unity. So that means k into B0 plus B1 plus B2 is equal to 1. So you can find the value of k because B0 plus B1 plus B2 is known to be 1.1366. So you can find k as 1 upon 1.366. So what it means is that each of these coefficients has to be multiplied by 0.8798 so that the array of the coefficients you get will ensure that the zero frequency gain is 1. So if you multiply each coefficient by k, then the result that you get is 0.28, 0.4399. So this is somewhat different than this. So when we write a small code and run it, we will see that the output of the program will be given by these coefficients and not by these coefficients. So just to revise, note that the array of coefficients that you get is slightly different because of the fact that MATLAB ensures that zero frequency gain is 1 and therefore it does the scaling. Okay, so let's look at the code. Now this following code uses the cutoff frequency f by fs equal to 0.25. So the parameter will be 2 into f by fs, so that will be 2 into 0.25, so that will be 0.5. Order of the filter, let's assume, is 2. Number of coefficients therefore will be n plus 1, that will be equal to 3. So let's now write the program. So this is as usual, you clear everything. N equal to 2, this could be something else, but right now we are assuming that the order is 2. So the number of coefficients that we will get will be 3. So now you call the function b equal to fir1, provide these values n, this is 0.5, low pass filter and the rectangular window. And then you display the coefficients. So when you do that, the result that you get is this. The result in the command window, it says the coefficients are 0.28, 0.4399 and 0.28 again. And these are the coefficients we had discussed in our last slide. This was the result we expected from our code and this is what we have obtained. Okay, now this is one useful function in the MATLAB which will allow you to obtain the coefficients directly. You don't have to do any analysis, just provide the parameters to the function and you will get your b coefficients. Similarly, you have another MATLAB function which is useful and that is for calculating the transfer function itself. In our previous sessions, we have actually written down the MATLAB program in order to calculate and plot the transfer function. However, our job is reduced a little because of the function that is available in the MATLAB. So that is called as frequency z function and there are 3 parameters to this, b, a and n. B is the array of coefficients. So you can first use the function in MATLAB for calculating the coefficients and then use that array as an input to this function. Now A is an input array which is actually required when you are designing an IIR filter, which we have not studied so far. We will do that in later sessions. But right now note that for FIR filters, you simply write A equal to 1 and don't worry about the rest of the A values. Later on when we study IIR filters, we will talk about the A array itself. But for now, A is going to be equal to 1. B, we have discussed that is passed. A we set to 1 and n is the number of points over which the calculations are done. And a typical value is 1024 because it's an integer power of 2. You could use some other integer power of 2. B, as I said, is the coefficients of the FIR filter. Okay, so these are the inputs to the frequency Z function. What are the outputs? Okay, so you get the complex transfer function which is returned in H and the angular frequency which is returned in W. So once you got this, you can plot the magnitude of Z as a function of omega, and you can also plot the phase angle of H as a function of omega. Okay. So let us now demonstrate a program using both the functions. So this is as usual, you clear everything. Now in this particular program, we are selecting a higher order of filter. If you remember, higher the order you use, better will be the filter response in general. That is between pass band and stop band, you will get a steep curve. Okay, so this could be something else also. You could use 10, 12 and so on. Usually the order of the filter is even, although it is not essential, but even order helps because it allows you to build a filter for any general kind of signal. Whereas if your order is odd, then you will find that there are certain constraints on the signals. So right now when we are going to test this program, we are going to test this only for even order of the filter, which means that the number of coefficients will be n plus 1, one more. So number of coefficients will be odd, the order will be even. Okay, then you obtain the coefficients. So call the FIR function, provide n, then provide the normalized cutoff. This says low pass filter and the rectangular window. So when this statement is executed, B coefficients are available. A, as we discussed, is set to 1. And now you can use the frequency Z function, which will enable you to obtain the transfer function H, complex transfer function, and the angular frequency values. So in this case, we are using 1024 points, frequency points. And then you can plot. So subplot 2 and 1. We are going to make two plots because one is the magnitude response and the other is the phase response. So subplot 2 and 1, W, absolute value of H. That will give you the magnitude response. Okay. Another thing you should note is this Y label. Note carefully what we have written here. So this is your normal colon, then this is normal H. This is again the normal bracket, and then you say E raised to. Now E raised to, if you want to obtain it as a superscript, whatever follows has to be written in curly brackets. And within curly brackets, what we have done here is J, and then remember omega is a symbol which cannot be used in your MATLAB program, so we use W. But when we are displaying the result, it will be useful if we actually display the omega. So how to do that? So you use this backslash followed by omega, and you will actually be printing the symbol omega and not this letters omega here. Okay. So note this. So similarly, you can explore, you can write, you can print many other kinds of characters. Okay. Then subplot 2 and 2, plot W, unwrapped angle H. I'll explain this, what we mean by unwrap, line width and the usual statements for plotting the graph. Now let us talk about the unwrapped and the wrapped phase. The wrapped phase is what we consider normal. That means if we don't write unwrap, the default is wrapped phase. Wrapped phase is phase angle modulo 2 pi. So this is the usual thing. See, whenever we write any phase angle, we go on increasing, and so you may go through pi by 2, pi, 3 pi by 2, etc. And then when you say 2 pi, you come back to 0. So the normal wrapped phase is a phase angle modulo 2 pi. Whereas unwrapped phase, which will keep on increasing monotonously as one round is complete. That is, you go through 2 pi, and then the next angle you actually add 2 pi. So you get a continuously changing value of the phase angle. So that will be wrapped phase multiplied by an integer multiple of 2 pi. So k is going to be an integer. So unwrapped phase, we are showing the phase angle by using unwrap because we want to show linearly changing phase. Otherwise, what will happen? If you use the default wrapped phase, your phase angle will start from 0. It will go to minus pi. Now from minus pi it will jump to pi. Again reduce to minus pi, and again will jump and so on. But if we want the curve to decrease linearly monotonically, because we expect that our filter is not going to distort the signal. We expect it to be a linear function of phase. We expect to be a linear function of omega. So if we want to see it clearly, you use the unwrap function. Otherwise you will get jumps. Okay. So now what about the delay provided by the filter? That is n by 2. Remember this. For example, if you have delay elements equal to 2, so coefficients are 3, so you got b0 plus b1x n minus 1 plus b2x n minus 2. In a situation like this, your order is 2, but you provide a delay of 1 sample, so that is 2 by 2. So in general, the delay provided by the filter is n divided by 2. So that will also tell you the phase angle, expression for the phase angle, that is minus omega n by 2. So if this of course is a function of omega, it's linearly related to omega. But if you calculate this at omega equal to 1 to check whether your curve is correct or not, then phase angle is simply equal to omega equal to 1, so is minus n by 2. In our program, we have chosen n equal to 10. So we should get that at omega equal to 1, we should get the phase angle equal to minus 5. That is the unwrapped phase angle. Alright. So let us now, when we execute this program, this is the result that we obtain. So this is the magnitude response. Remember our cutoff frequency was pi by 2. So really the range of interest is from 0 to pi by 2. This entire plot is from 0 to pi. Note that 3.14 and so on. So range of interest is really from 0 to pi by 2. And you can see that in this case the unwrapped phase response is continuously decreasing linearly. And at omega equal to 1, you get minus 5 as calculated. Okay. But if you plot this without using the unwrap function, then what you will see will be jumps in the phase. So you start from 0, goes up to minus pi. From minus pi, it jumps to plus pi, again starts decreasing and so on. So if you want to see the monotonically decreasing phase response, which is satisfying to us, because after all, for no distortion, we want that the phase should be linear function of frequency, and that is clearly seen when we have the when we plot the phase angle using unwrapping. All right. So in this particular session, we have studied the filter function, which enables us to calculate the FIR filter coefficients for any of the filters: low pass, band reject, high pass, and so on. And we have also studied a function which enables us to obtain the transfer function and plot the magnitude response as a function of frequency, and also plot the phase response as a function of frequency. And we have distinguished between the unwrapped phase angle and the wrapped phase angle. And that's all in this session.